Chapter 21, electric current and direct current circuits. So electric current is a flow of electric charge from one place to another, okay? And the definition of electric current, or I, is thus I is delta Q over delta T. So you have a change in the number of charge over a change of time. And the unit for that is Coulomb over second, or Coulomb per second, which we call it ampere, or A. The closed path through which charge can flow, returning to its starting point, is called an electric circuit. So if I start from this point, all of my charges are flowing this way, going all the way and coming back to the same point that they started. I call it a closed circuit, or a circuit. And along the way, there could be different things that happens to this charge. But if it starts from one point, going all the way back to the same point, we call it a closed path or electric circuit. Here, I have a change of charge over a change of time, and I call that current, or I. So current, the number of electrons passing a given area per second. It is a fundamental quantity with the units of ampere, as I said, is 1 coulomb per second. And if the rate, because this I is delta Q over delta T, if this rate, because this is the rate of change, right, is constant, then delta Q over delta T is a constant value. Okay, that means that I at each moment and I of average are the same, because you're having a constant rate of change for a value. So it's average and its spontaneous value should be the same. And the charges always flow through the circuit in the same direction, okay? When we have a DC current, or direct current, okay, if the charges change direction in the circuit, we have an AC current, or alternative current, okay? So DC stands for direct current, and AC stands for alternating current. So how does it work really? So what the battery is doing is that it's creating a potential difference between 2 points. For example, here I have a battery, one side is positive, the other side is negative. And what this battery is doing is that it is creating a potential difference between 2 points. For example, between this point and this point. This point is connected to the positive, and this point is connected to the negative. So whatever that this battery is, for example, let's say that it is 12 volts, then the potential difference between these 2 points are 12. Okay, this will cause the electrons to move from a higher potential to a lower potential. So this is the path of the electrons. So these are all of my electrons going. On their way, for example, I have a light bulb here. Because of they are passing through this light bulb will start to shine. Okay, the reason for that, the reason for this path and this direction of motion of these electrons is that we have a potential difference between 2 points. Essentially, it's the same idea if you have a paddle wheel. So when you are having this water going all the way up, going to a higher potential, gravitational potential at this point, okay? So from point 1 all the way to point 2, point 2 has a higher potential, gravitational potential energy. And so when you release this water, it will go all the way to the 0 level, or to level 1. So the fact that we have charges going through this circuit is essentially the same thing that you can see here. You are bringing it to a higher potential energy, releasing it, it will go all the way to the lower potential energy. So what we have is from the high potential we'll have things, water, electrons, charges going to low potential. Okay. So electromotive force. First, it's not a force. Okay, we call it force, but it's not a unit of Newton, so it's not a force. All right. It is defined as the maximum potential difference. Maximum potential difference between the terminals of a battery, and we call it with E. We show it with E or you know, omega or epsilon here. But sometimes books have shown it with E. Sometimes have shown it with small e, little e, or they call it epsilon. But regardless, it's the maximum potential difference between the terminals of a battery. The terminals of a battery are held at a potential difference, for example, of 12 volts, by converting the chemical potential to the electric energy. So if I have a battery here, okay, let's say a car battery with a 12 volts. So I have a positive side plus, I have a negative side minus, and this is always held at 12 volts difference between positive and negative. This is coming from the chemical reactions, chemical potentials that are converting these electrons to go to a higher potential when they are released. So converting the chemical potential to electrical energy. That's what the battery is doing. The terminals are connected to wire that supply current to the device needing electricity. So then you can have this battery connected to your device, let's say a lamp or a something, and then this, you can use this device because it's connected to the battery and charges are going through this device for us. An electric field exerts a force on electrons in the wire, causing them to move. This is the exact same truth. The reason that these charges are moving from a higher potential to a lower potential is because there exists a field, electric field, and that electric field is causing the electrons to move. So the terminals are connected. The electric field exert a force on electrons. So this is very important. All right. Now, the amount of work it takes to move a charge, delta Q, from one terminal to another, is delta Q times E, and this E is electromotive force. So in other words, if you want to find the electromotive force, you need to know the work done and divide that by delta Q. Okay, divide that by delta Q. So keep that in mind. This is also very important. Okay. Conventional current. Again, I've talked about it back in chapter 20. I want to talk about it here as well. This is the point that book talked about it, so I want to talk about it here as well. For historical reasons, conventional current is defined as a direction of positive charge, as a direction that positive charge would flow through the circuit. So what we have is that this positive is going, the electrons or the charges are going from positive all the way to negative, a higher potential to a lower potential. This is called conventional current. But the electric or electron flow or the actual current is from negative to positive. It is actually electrons that move through the circuit from a lower potential to a higher potential, because we know that electrons are free. They can move from one atom to another, but protons that are positive are fixed. They are inside atoms and the atoms are fixed, okay? But the amount of charge shouldn't matter anyway. Does not matter if you think that your current is in this direction or in this, or is in this direction. It doesn't really matter. The amount of current is delta Q over delta T. Okay. So either way, this value is constant. I will always use conventional current, okay? Now, a word about this I, which is equals to delta Q over delta T. If I am looking at this shape and I think that this shape is a view of a wire, okay? So let's say that I am looking at a view of a wire, kind of like that, all right? So what I have here, this is the cross section of a wire. You're looking at a wire right now. And what we have here is that let's take this cross section inside the wire, okay? So if this is just a normal wire, not connected to any potential, not connected to battery, you have all of these electrons that are freely moving around. So these are all electrons, okay? They go in all directions, everywhere. They're not necessarily, followed any kind of a direction. So if you consider that, then on average, the number of Q, or the number of charge, going past through this cross section is 0, because if 2 of them are going to the right, then 2 of them will go to the left. So if you have 2 electrons going to the right, okay, 2 electrons, then you have 2 electrons going to the left, okay? So on average, there is no net charge passing through this cross section, okay, or this shade area, this area that I showed with blue. So that's why there is no current in a piece of wire. But if you connect this to a battery, okay, if connected to a battery or a potential, so if connected to potential or battery, okay, then this cross section, the amount of charge passing through this cross section is not 0 anymore, because all of these electrons are forced to go in one direction. All of these electrons are going in one direction, because there's a positive here and there's a negative here. And there is a force because of there is an electric field inside, so that all of these electrons are moving to one side. Now, what does it mean? It means that at this point, I, which is delta Q over delta T, is not 0 anymore. The amount of charge passing through this cross section is not 0 over time. There is a net amount of electrons passing through this cross section, or this area, at a unit of time, and this is not 0. Okay, so that's why you have a current at that point. Okay, let's take a look at this example. The current in a toaster is 12 amperes. So I is 12. Okay. And how much charge passed through the toaster in 1 minute? So what this 12 is telling me is that I have 12 electrons, or 12 coulombs, okay, per second in 1 second. This is exactly what it means, coulomb per second ampere. Okay. Now I want to know how much in 1 second we'll have 12. Okay. Now for 1 minute, or 60 seconds, I have to multiply that by 60. Okay. So what I have is that this second and this second will cancel out their units, and I am left with 12 times 60. 12 times 60. The unit for that is coulomb. Okay. So in this case, I is 72. 720. Okay. So let's take a look at B. How many electrons pass through the device in 1 minute? Now we were looking to see how many electrons. We know that this Q, okay, and by the way, this is not I anymore, so I wanted to show it with Q, because this is in the units of Coulomb, and this is Q, not I anymore. So Q is that. Okay, now part B, we know that Q is N times E. So Q is 720. N is a number of electrons. Electron E is 1.6 times 10 to the negative 19. Okay, so now we're solving it for N. N is 720 over 1.6 times 10 to the negative 12. Whatever it is, you can put it in your calculator. Find the number of electrons that are passing through, that are causing 720 coulombs. Current, resistance, and voltage. So just like more pressure causes more water through a pipe, more voltage causes more current to flow through a wire. Okay, so one more time, more voltage causes more current to flow through a wire. If you have a 12-volt battery compared to if you have like a 2-volt battery, okay, the 12-volt battery will produce more flow of charge in your circuit or in the wire. Okay, so also the size and shape of a pipe can affect the amount of water flowing, right? So the size and the composition of the wire, if it's a copper, if it's a gold, if it's aluminum, whatever it is, affects the amount of current flowing through the wire. So not only the size of it is important, but so what type of a composition it has. We refer to this as electrical resistance, okay, or R. We show it with capital R. Resistance is measured in ohms, and ohms is 1 volt. 1 ohm is 1 volt per amp. Okay, so in other words, V is related to I, okay, and V is related to 1 over R. We'll get to that in a second. Both of them, not 1 over R. This is related to R. I is having a reverse relationship with R, not V. V is equals to IR. So if I want to write it in these two in a law, this would call the Ohm's law. So under normal circumstances, and I'll talk about what the normal circumstances is, okay? Wires present some resistance to the motion of electrons, okay? Because these electrons, as these electrons are moving in a wire, they will be captured by these atoms in a way, okay? So some of them will stay, some of them will trap by the potential of these protons in a way. So it's not like that they are moving freely. There are some resistance on their way. Ohm's laws relates the voltage to the current. So in other words, as I just showed over there, V equals IR. Voltage equals I, which is the current, times the resistance, which is in ohms. Okay, so here's a word of caution. Ohm's law is not universal law. It's not always true, and is only useful for certain materials. Okay, so this law is not something that will always be true, depending on the temperature, depending on the materials that we're talking about. But for majority of materials, for conductors, for most of the conductors, the Ohm's law is true. So suppose a 12-volt battery produces a current of 1.2 amps in a headlight. what's the resistance of the headlight? So let's write down what we have. We have a 12-volt battery, so the voltage is 12. Produces a current of 1.2 amp. So I is 1.2 amps, okay? And we'd like to know what the resistance is, R. So we know that Ohm's law is telling us V equals IR, okay? So V, which is 12, equals I, which is 12, which is 1.2, not 12. This is 1.2 times R. Okay, so if you want to solve it for R, R is then 12 over 1.2, which is 10. So R in the units of ohms is 10. So more on Ohm's law. Let's go a little bit further in. So the form of the equation that we have, V equals IR, this looks familiar. This is a linear equation, okay? So in other words, if you plot V on y-axis and you plot I on x-axis, if you do that, then you will end up having a linear relation between V and I, which is this, okay? And the slope of this, okay, so the slope, which is the tangent of this angle, would be R, or resistance, okay? So any resistor that follows Ohm's law is called ohmic, okay? We can determine the resistance of any resistor by measuring the current passing through the circuit for a given example. So if we know the voltage, and if we can measure the current, we can easily find the resistance of the circuit, or the device. But if you have voltage versus I figure, it will have a linear relation, and the linear relation will give you the R, or the resistance. So let's go over this example. Ohm's law, you double the voltage, okay, across a certain conductor, and you observe the current increase 3 times. What can you conclude? So Ohm's law is telling me that V equals IR, okay? R is the resistance of the wire. It's always the same, okay? So it is independent of this. If you increase this voltage, then your current should increase as well in order to keep the R constant. So in other words, R, which is always a constant value for a device, V over I. If you multiply this by 2, you need to multiply this I by 2 as well, so they can cancel out. So you have the same constant value over here. If it's not happening, then you're not having an ohmic relationship. Your wire is not ohmic wire. So let's take a look at these options that we have. Ohm's law is obeyed since the current still increases when V increases. That's not true. Ohm's law is not obeyed. This has nothing to do with Ohm's law. Ohm's law is not obeyed for sure. So that's the correct answer. Resistance and resistivity. So the resistance of a wire depends on its length. So length is important. Longer, more resistance. And the cross-section area, which is A, which is right here, L and A. And that's the relationship in there. So R is rho L over A. This L is the length of the wire. This A is the cross-section area. The cross-section area is this. Let's see that this is our wire. And this is L, and this is the cross-section area, which is A. And then we have something called resistivity, which we showed with rho. So the resistivity of rho. This depends on type of a material that we are using. Depend on if it's a gold, if it's a copper, whatever the material that we have an individual rho for that. So it depends on the material. Insulators have a higher resistivity, okay, than conductors, because the conductors are conducting very well, but the insulators don't. So I hope that makes sense for you. Semiconductor are materials that have resistance value between conductors and insulators. So now let's take a look at some of these numbers. So for insulators, we have these different, for example, glass, which is actually very high number value. So let me write down the formula here. R is rho L over A. This is the resistivity. So for example, rubber is 1 to 100 times 10 to the 13. So this rho is a high value, and the R is actually high. So that's why it's really difficult for charges to move. So that's why they don't move charges with them. Semiconductors are between conductors and insulators. And conductors, for example, copper, silver, gold, aluminum, whatever, iron, then you can see that this number for rho is actually a very low number. It's a very small number because it is very high conductivity, causes to this number to be really low. So resistance and extension cords. So have you noticed that longer extension cords are thicker? But why? So we want to maximize the amount of current that flows, to our devices. But the voltage of the outlets that we use here in the United States is 120 volts. If you go to Europe or if you go to Asia, it's different. It could be 212. But these are also AC currents, okay? So 212 or 220 or 120. In the US, we have 120, okay? If the resistance is lower, more current can reach to the appliances, right? So thicker cords have the large A than thinner cords. So let me write it down. R is rho L over A. Okay, so if you have a very thick wire, in other words, this cross-section area is high, that will cause your R to be very small. Okay, on the other hand, if you have a very thin wire, okay, then resistivity will go up. So if I want to have a very long and a very a very long extension cord, in order to keep, if this extension cord is very long, okay, that means this L is high. In order to keep the R in a reasonable value, the resistance in a reasonable value, I have to make it thicker so that this will stay, this ratio will stay unchanged, okay? So that's why the long extension cords are also thicker, because we want to have them to have a low resistivity in order to keep R small. So we have a 20 gauge extension cord that is 35 meters long. So, and a 16 gauge extension cord is 50 meters long. The cross-section area of the 20 gauge cord is 5.2 times 10 to the negative 7 meters squared. That's a cross-section area, so it has to have a meters squared as its units, which for the 16 gauge cord is 13 times 10 to the negative 7. Both wires are made of aluminum. How do their resistance compare Okay, so I'm not going to put the numbers in my equation, but I'm just going to show you how you need to do it. If you want to compare, if you see a word compare in physics, what you need to do is to make a ratio out of them, R1 over R2, okay? R1 over R2. R1 over R2, let's write it down. Rho 1, L1, A1. Rho 2, L2, A2. Okay, so what we have here is this. Rho 1 over rho 2 times L1 over A1, L2 over A2. I can write this as this. Rho 1 over rho 2 times L1 over L2 times A2 over A1. So that's how you can compare R1 with R2, to make a ratio out of them. If they are the same materials, which in our case they are, they're both from aluminum, so that means that your rho will cancel out, and then it only depends on L and A. So that's how you can compare them. Just put the numbers here for L1, L2, A2, and A1, and compare R1 and R2 to find out what the relationship is for them. Wire diameter and resistance. So two wires, A and B, are made of the same metal. The same metal means that they have the same rho. Okay, so the rho is the same for both of them, and have equal length. But the resistance of wire A is 4 times the resistance of wire B. How do their diameter compare? So, we want to compare their diameter. Let's write the same thing that we know, that rho, or R, is rho L over A, okay? And they are the cross section, or A, okay? If this is R, R is D over 2, or diameter over 2, okay? And then an area is pi R squared, okay? Or the area is pi D over 2 squared. Okay, so if you want to compare that, then you have R being rho L. For A, I can write pi D over 2 to the power of 2. So you'll have D squared over 4, and I can bring that 4 up. Okay, so in other words, you have 4 rho L pi and D squared. Now, if you want to compare that, you will have R1 over R2, 4 rho 1 over 4 rho 2 times L1 over L2 times pi will cancel out, right? So you'll have D2 over D1 to the power of 2. Now, they're in the same metal. They have either, the composition will be the same, so this will cancel out. So you are left with R1 over R2 being equal to L1 over L2 times D2 over D1 squared. Now, what it says that two wires of A and B made of the same metal and have the equal length, so L1 and L2 is the same as well. Okay. And the resistance of wire A is 4 times the resistance of wire B. So, in other words, this ratio, R1 over R2, is 4. Okay. So R1 over R2 is 4. In other words, this ratio to the power of 2 is that. So you have D2 over D1 being equal to 2. In other words, D2 is 2D1. So, or if I want to show it with A and B, this is dB to dA. Or that's the correct answer right there. Okay. So let's go to another example, resistivity and wire length. A wire of resistance R is stretched uniformly, okay? Stretch uniformly. What does it mean? It means that the volume is constant. So the volume of the wire in shape 1 should be equal to the volume of the wire in shape 2. So you stretch it uniformly until it is twice its original length. Okay, so in other words, L2 is 2L1 because it's twice its original length. What happens to the resistance? So what we know is that the R, or the resistance, is rho L over A. That's the formula. Okay, so for R1, you have rho L1 over A1. Okay, for R2, however, you have the same rho because it's the same metal, it's the same thing. Rho L2 over A2, or rho L2 is 2L1, so instead of L2, I'm having 2L1 here, and A2 here. But let's find what A2 is. So we need to know what this A2 is. It has the same volume. In other words, if this is our wire, then the volume for this wire is L times A. So the volume is length times the cross-section area. Okay, since V1 and V2 is the same, so L1 A1 should be equal to L2 A2. So L1 A1 is L2, but we know L2 is 2L1, right? 2L1 A2. So this L1 and this L1 will cancel out. And then we are left with A2 being A1 over 2. So I can use that right there. Okay, so I have rho 2L1. For A2, I have A1 over 2. So R2 is, this 2 times this 2 would be 4. 4 rho L1 A1. But we know what this rho L1 A1 is. We know it from here. It's R1. So we know that this guy is R1. So in other words, R2 is 4R1. So R2 is 4R1 by a factor of 2. It increases by a factor of 2 right there. Impedance plethysmography. So I'm not going to read all the information to this slide, but essentially this will help you if you were in the pre-med, to understand how you can find the blood clot. What it's essentially doing is that we have an area, designated area here, and it has a volume associated with it, which is right there. Okay, and then this volume, if this volume increases, goes up, since it's in the denominator, you have the resistance to go down, to decrease. Okay, when you have unclotted veins, once you remove this pressure, this R will go back to the normal very quickly. But if you don't have, and in fact you have some clotted veins in your body, then this will not go back to normal quickly. So that's one of the ways that they can identify if you have a clot in your blood. Resistance and temperature. So resistivity depends on temperature. As I said, it's temperature dependent. Rho increases as temperature for conductors and decreases as T increases for semiconductors. So it increases as T increases for conductors. It decreases as T increases for semiconductors. And we have that kind of a relationship here. So rho equals rho 0, 1 plus alpha T minus T0. T0 is the initial temperature, T is the final temperature, R is R0, 1 plus alpha T minus T0. T0 is again the initial temperature. We have the same relationship for R because R is no difference from rho. See, if R is rho L over A, so in other words, R is related to rho. So whatever that happens to rho will happen to R. So that's why you have the same relationship here, okay? Alpha here, right there, okay, is called temperature coefficient of resistivity. It's usually be given, depends on the materials. Usually if you're dealing with a problem that has temperature inside, we usually give this to you, or this could be an unknown, and we'll ask for it. So superconductors are materials whose resistivity goes to 0 below a particular temperature, or T of C, a T of critical. This means that once a current is applied, it continues even after the EMF, electromotive force, is removed. So even if you remove the battery, you'll still have a current going on because there is no resistivity, there is no resistance. Okay, remember that V equals IR. Okay, if you remove this V, in other words, if you remove the battery, if you remove the electromotive force, since there is no resistance, this current, these electrons will try to complete the circle, complete the circuit, a closed path without any problem. In contrast, current in non-superconducting materials almost immediately goes to 0 after the EMF is removed. This is something that would make sense right now when you're thinking about it. If you have your cell phone disconnected from a battery or disconnected from charger, since there is no potential, there is no voltage, there is no current. As soon as you remove your phone from the charger, you see that there is no current inside your phone. It's not charging anymore. This is immediately happens. But for for superconductors, it's not like that. Superconductors can have current without any EMF applied. So when a charge moves across a potential difference, what does this potential difference means? It's just a battery from positive to negative. Its potential energy changes, and this is something that we have seen before, right? We saw that V was U over Q. So, okay. So what we have here is just a change in the U equals the change of the Q times the voltage, if this voltage is, let's say, something constant. Therefore, the power it takes to do this is delta U over delta T, and I can replace this delta U with this, what I have, this equation up here. Okay, so delta Q times V, and then delta Q over delta T, we have seen this before, don't we? Have we seen this somewhere before? This is current, isn't it? So power is VI, or I times V, does not matter. And the unit is watts. That's the power of doing this. Remember, the power, if you remember from chapter 5 of physics 1, P, or the power, is work done divided by the time it took for the force to do the work. And here, work is change of the potential energy, as this is a non-conservative force, and over time, and then you have delta QV for delta U, and the rest is the same. So P is VI, all right? Not only that, but I can remember that V equals IR, isn't it? So I can combine these two and write it in different ways. Okay, and each way has its own features. So if I combine these two, I can write P being equal to V. Instead of I can write V over R. So you have P equals V squared over R. I can write V as IR and put it right there. So I have IR times I. So you have RI squared. And then I can write it as if we write it like this. V times I, same old formula. So you have three ways of showing the P, or the power, and each will give you something special. I'll talk about that in the next couple of slides. So let's take a look. How does electricity work? So a cell phone receives power via battery. Charge leaves the positive terminal of the battery and flows through the cell phone. As it flows through the phone, it loses EPE, or electric potential energy. Okay, energy is conserved, we know that, and the EPEs is converted energy, lighting the LED screen, sound energy, speaker, thermal energy. Your cell phone is, if you play a video game with your cell phone will heat up. When the charges reaches the negative terminal, okay, in your battery, when you charge the negative reaches the negative terminal, it gains EPE as it sends through the battery. So the energy gained is taken from chemical potential energy from the battery. Now, if you misuse your battery, you will technically messing with this chemical potential. And if you go to your cell phone, you can see what the life of your battery is. For example, mine is right now 82%, which is not very good. But you can check on that to see if your battery is doing a good job. These chemical reactions are doing a good job putting back electrons to the higher potential and leaving them. So electric devices can be thought of resistors that heat up when provided with enough power. We can write power in terms of resistance using Ohm's law. So if you remember, I wrote it in three different ways, which you can see on your screen. And so P equals V squared over R, P equals RI squared. And these two have different usage. So if P is Ri squared is used to describe the power that is lost. Okay, so P is Ri squared is a lost power, okay, due to the heat through a resistor such as wire. But P of V squared over R is used to describe the power that is provided to the resistor. So this is provided, okay, to the resistor, or not specifically resistor, it could be appliances, it could be, you know, a wire. But so when we're talking about the lost power, use this, P equals Ri squared. When you were talking about the provided power, we talked about PV squared over R. Okay, let's take a look at this example. Example number 4. What is resistance of a 60-watt light bulb designed for use in 120 volt circuit? So we know that the voltage is 120. Okay, and we know that the power for this light bulb is 60 watts, okay? In other words, this is changing 60 joule of energy per second for us. So we have both of these values, and we're looking to find the resistance. So we're looking for R, and as well as current. So we know that P is V squared over R. We know that, right? It's one of our formulas. So let's put some numbers in there. We have 60 as our P. V squared is 120 to the power of 2, okay, divided by R. So 60 is 120 to the power of 2 over R. And then thus R is 14400 over 60. And if you do that in your calculator, if you put that in your calculator, you have 14400 divided by 60, which is 240. What's the unit for that? Ohms. Okay, now that you have R, so you technically have gotten that, and then you know that P is, you know that from Ohm's law, V is IR, right? So V is 120, I is unknown, R is 240, okay? And then I would be 1 over 2 current of amp. So half amps would be your current, or I. Okay, this is the end of part 1. We'll go to part 2 right after this.